Welcome to the fifth lecture of the series of lectures on kinetic theory and thermodynamics. This lecture hour will be essentially spent on describing the basics of thermodynamics, but as our regular practice is, I will be doing a little bit of recapitulation of kinetic theory of gas. What we did in the last lecture, we talked about mean free path and non-ideal gas. Both the things I will touch upon briefly before I move on to thermodynamics. So, we calculated the mean free path. What is this quantity? This quantity is the distance traversed by a molecule between two successive collisions. Since we are talking about kinetic theory, I need not remind you this is the average distance. And this quantity is actually given in terms of average velocity and time between two successive collisions, which we calculated, and that gives me the mean free path, which is 1 by n pi d square, where d is the diameter of the molecule and n is the number density. Now, here we assume that molecules are Herd spheres with a diameter d. Then what did we do? We constructed a cylinder this is the height and this area is pi d square and molecular diameter is this d and this radius is d. Okay. Now, we draw this picture. This is the top view of this cylinder, if you like. This is the molecular radius d by 2 and this is the radius d of the cylinder I have constructed. So, what is important is whenever any other molecule, let me remind you that I assumed other molecules are static in the beginning. Whenever the center of any other static molecule comes here, tries to penetrate this cylinder, there is a collision. So, whenever any other static molecule has its center either on this line or inside, that is inside the bigger cylinder, there is a collision. Using this, we could calculate the total number of collisions in time delta t. Total number of collisions, we found out that it is n pi d square delta t. This is total number of collisions over a time delta t. From that, one can easily find out what is the time between two successive collisions and hence the mean free path, which has this form 1 by n pi d square. So, it is important that molecule has a finite size and that is taken into consideration while calculating this mean free path. Now, there could be many questions here. This target molecule which I mentioned in the last lecture, it suffers collisions, though it gets deflected, right? It should be deflected because it is having collisions. If it has collisions, then can I talk about a single cylindrical geometry which I am mentioning here? It is not actually the fact. Of course, it gets deflected, but on an average sense, locally I can assume still there is a cylindrical geometry and whichever static molecule does have its center lying within the bigger cylinder will suffer a collision. So, on an average I can assume there is a cylindrical geometry of area pi d square and height v delta t. So, this gives me the expression for mean free path. There is an additional approximation. That approximation is other molecules are static, which is never the case. One should not take V average, rather one should be taking relative velocity between two molecules under consideration. If you do things in a more rigorous way, you will find out a correction of factor of root 2 coming into the expression of mean free path. So, I wanted to emphasize the following point, that we are making an assumption that on an average there is a cylindrical geometry, even if my target molecule is suffering many collisions. Now, then we went to non-ideal gas. Non-ideal gas is a van der Waals gas. For van der Waals gas, the equation of state for 1 mole of van der Waals gas is given like this. Okay? So, this is very important that you note that there are two corrections. One correction is A by V square, other correction is B. Okay? First correction, as I told you, is a correction to pressure, and this fellow A by V square must be having dimension of pressure. Where does this correction come from? I told you that I am assuming molecules are completely non-interacting, but remember there is a weak attractive interaction between the molecules. This A by V square captures that. It is actually the average of these attractive interaction. I gave more specific example by saying if a molecule hits the wall, is at the wall, this molecule will be pulled by an attractive force by all the other molecules which are inside the container, and number of molecules which are on the wall at any instant will be proportional to n by V. Similarly, number of molecules which are inside the container will also be proportional to n over V. So, average correction to pressure will be of the form constant by V square. So, this correction arises due to attractive nature of interaction which is very weak, and when a molecule is inside the container, I can conclude that on an average this is 0, but when it is at the wall there will be an attractive force which effectively corrects pressure. Now, second correction was B. Why does B come? B comes because of the fact that molecules, as I also had explained in the case of mean free path, that molecules are of finite size. We assumed they are actually Hertz spheres of diameter d. In that case, I explicitly calculated with some phenomenological arguments that B should be proportional to 4 times number of molecules in the container and then volume of a particular molecule, which I calculated. I showed, assuming they are spherical molecules, this expression is 4/3 pi d by 2 q. This is the volume of a molecule. Okay? So, B is proportional to volume of the molecule. What does B represent it for us? B tells us if I take a molecule, the entire volume is not accessible to it. Each molecule has a volume which is excluded. I said if this is a molecule and took 2 molecules, I can assume a spherical, concentric spherical volume which has radius d, which is excluded for the other molecules. Okay? So, excluded volume correction is incorporated in this parameter B, and I have my van der Waals equation of state which is P plus A by V square, correction to pressure due to average attractive interaction. B, correction to volume, because the entire volume is not accessible to the molecule. Each molecule has a finite size, hence a finite amount of volume will be excluded for any molecule I have in consideration, and then this B will be naturally proportional to number of molecules I have in the container and volume of each molecule. Okay? That explains the origin of A and B. Now, if someone wants to generalize to n moles ideal gas, we know PV is equal to nRT. So, what should be the form in the case of van der Waals gas or the real gas? Let us assume n moles. Okay? For n moles, you know correction to volume will be more, because I have more molecules now in the same volume. So, my excluded volume will be n times more. Excluded volume will be n times more. Okay? That is what is reflected V minus NB, and then here also density goes down by a factor of n. So, it is n NV into n by NV. So, you will be having a n squared term coming here. So, your van der Waals equation, I write it down again, will now turn out to be V minus NB is equal to nRT. When the limit A going to 0, that means when you ignore, you are allowed to completely ignore the interaction, this attractive force A is equal to 0, when you can assume the point particle nature of the gas molecules, then you can ignore B, and when you set A is equal to 0 is equal to B, you retrieve your ideal gas equation. Okay? But these two corrections are very non-trivial corrections. Okay? And these allows us to explain the phase transition. For example, the liquid gas phase transition that we often talk about and that we encounter in our real life. Okay? So, having said that, I wanted to bridge a connection between the van der Waals equation of state and the phase transition, liquid gas phase transition. Okay? So, I drew the isotherms. What are isotherms? I fix the temperature. Okay? I fix temperature, plot pressure as a function of volume, and I claimed these are the curves. Well, I wanted to note something here which I did not intentionally mention in the last lecture. If you really plot van der Waals equations mathematically, you can use it in your computer, you will see the curves are not really like that. Typically, a isotherm will look like this. Okay? Without much explanation, which is far beyond your syllabus, I will say there is something called Maxwell's construction which gives this form, which I have drawn, and this form is experimentally verified. What I said here, there are different temperatures T1, T2, Tc let us say, and this is term T3 which is greater than Tc. Temperature is increasing, so T2 is greater than T1, Tc is greater than T2 and so on. So, there is a liquid phase which is high pressure, low volume. There is a gaseous phase which is high volume, low pressure. So, I can go from one phase to the other by changing temperature or by changing pressure, but there is a difference. There is this temperature Tc and I drew a dotted line here. I said This region is actually the coexistence region in which liquid and gas coexist. I have to correct myself. Liquid and vapor coexist. Why it is important? Because I gave you the definition of vapor. Vapor is the gas below this critical temperature Tc, as I repeatedly mentioned, above the critical temperature Tc, which is this T3. Remember, I am plotting isotherms P as a function of V for different temperature. So, if I look at the isotherm at the temperature T3, which is higher than Tc, no amount of pressure can liquefy the gas. It is always in the gaseous state. So, liquefaction of a gas by application of pressure is not possible if I am at a temperature which exceeds the critical temperature. So, van der Waals equation, two simple corrections, we gave two simple corrections, one to pressure coming due to the fact of attractive interactions. Finite size gives one more correction, that is correction to volume. Very phenomenologically, I explained the origin of these two corrections. These correction terms have drastic effect on the physics I am studying. It explains liquid gas transition. You see, through a coexistence region, okay, below Tc there is a coexistence region. I change pressure, I go from liquid phase to the gaseous phase or the vapor phase through a coexistence region in which liquid and vapor coexist, and above the critical temperature no amount of pressure can liquefy a gas. Okay? If you like, one can draw a P versus T diagram keeping volume fixed. You can see it coexists on this coexistence line that ends at this critical temperature. Okay? This also I explained. So, phase transition can only come through interactions, and van der Waals equation, simplest possible correction to ideal gas equation, gives us phase transition, which is very, very important. Having recapitulated whatever I said in the last lecture, I will be now moving on to describe thermodynamics and basics of thermodynamics. There is a fundamental difference between kinetic theory and thermodynamics, which I explained in the very first lecture. Thermodynamics is a macroscopic approach to understand the properties of matter. Macroscopic approach. What do we mean by that? I do not care about what is happening at the molecular level. I do not care about the velocity distribution or speed distribution or average velocity. All I will look at is experimental measurable quantity. Okay? I will be looking at only pressure, volume, temperature, which I measure experimentally. So, it is a coarse grained description in that sense, which I mentioned. That means, I am looking at the macroscopically measurable objects like pressure, volume, temperature. Remember, in kinetic theory also, we are talking about average speed, average velocity, but eventually everything was connected to pressure, volume and temperature. So, kinetic theory had its own definition of temperature, that is given in terms of average kinetic energy of the molecules. Similarly, thermodynamics will have its own definition of temperature, but it will be again connected to experimentally observed temperature in absolute or Kelvin scale, which I introduced in the very beginning of this set of lectures. So, it is a coarse grained description, does not probe the system at the molecular level. We do not care what is happening at the molecular level, and that is why I call it a macroscopic approach. So, PVT, these I will call thermodynamic variables. Well, you know degrees of freedom in mechanics, you learn degrees of freedom, position and momenta. When I discussed equipartition theorem, I talked about x and p both contributing half kT to the energy. Here in thermodynamics, there is no x, no p. All degrees of freedom I will be talking about are p, v, t, and there are other quantities for other systems, but we will restrict ourselves to p, v and t. Okay. Now, basic idea is this thermodynamic approach talks about a system plus the rest of the universe. So, I will have a system which my experimental system and then the rest of the universe which is interacting with the system. Okay? This is very important statement. So, I will have a system, this is my S, and then I will have the rest of the universe which I will call the reservoir. Okay? So, I have a system and a reservoir and they are separated by a wall. Okay? So, you see the difference. I do not know what is there, what molecules are doing, but I know there is a system which is described by pressure, volume and temperature, maybe chemical potential, let us not go into that. And this is separated from the rest of the universe, whatever else is there in the universe, with some wall. And these walls play a very important role in defining thermodynamic variables, which I will come soon. The walls determine what type of interaction the system will be having with the rest of the universe, which I will simply call universe subsequently, and the equilibrium that system reaches. Now, since I mentioned thermodynamic variables, I must say that they are of two kinds. One is extensive, other is intensive. Let me define what do I mean by extensive and intensive thermodynamic variables. Let us take a big system described by N, V, T, P, and things are in equilibrium, which means that nothing depends on time. So, they have a fixed value, constant in time value. Now, if I divide it into two halves, what is the volume? V by 2, V by 2. Okay? Now, volume is halved. What happens to number of particles? I am assuming the system is divided into two equal halves in equilibrium. So, whatever equilibrium was there before I am making this division, that equilibrium is maintained. So, if pressure was P here, that let me see, this is the container, one of the wall of the container, this pressure was P for equilibrium. Okay. So, pressure will remain the same when I divide into two halves. Temperature again, if I have to keep things in equilibrium, that is nothing depends on time, temperature should not change, but you see V goes to V by 2. Similarly, N goes to N by 2. So, you see that there are some quantities which become half of their initial value, there are some quantities which are not at all influenced or affected by this division of the system into two halves. Okay. Quantities which are indicative of system size, that means if I have the system, they get halved, they become half of their initial value. These are called extensive quantities, for example, volume, number of particles, and also a quantity which I am going to define very soon is called the internal energy. these are extensive quantities. Okay? For example, if I define external energy, it is a function of volume, sorry, this is the internal energy. The internal energy which is a function of volume. If I increase the volume by a factor x 3 times more, so volume, let us say volume goes to x volume, x can be any number, it could be 2, 3, half in the present example. Internal energy actually will show that goes to xu. These are extensive quantities. Maintaining equilibrium, you make the volumes x times the initial value, the internal energy, number of particles, they all go x times. Internal energy u goes to xu. Let me be more precise. I am saying increase the volume of the system maintaining equilibrium. The simplest way to think that I am considering a bigger volume of the same system, okay, as I have shown in this example. Henceforth, whenever in the context of extensivity, I say increasing the volume, maintaining equilibrium, I mean I am considering a bigger volume of the same system. Question is, what are other types of variables? These are intensive. For example, pressure, temperature, they do not have any change because of this multiplying by a factor of x. So, these are intensive quantities. So, intensive quantities are completely insensitive to the size of the system, whereas extensive quantities are indicative of the size of the system. Maintaining equilibrium, if I double the system, all these extensive quantities will become double. But there is an interesting thing, density. What is density? Density is n by v. Okay? If volume goes to x, v, number of particles, which is also an extensive quantity, will go to xn. So, x cancels with x, you see density remains the same. So, density is an intensive quantity, true for any ratio of two extensive quantities. Whenever I take the ratio of two extensive variables, that becomes an intensive quantity. Okay? So, this was important to tell you that thermodynamic variables, they describe entire thermodynamics and they are of two types, one intensive and other is extensive. Having said this, let us go to the walls. I told you I will be having a thermodynamic system and this thermodynamic system will be separated from the rest of the universe or simply the universe as I will say it, and this is my system separated by a wall. Okay? These walls will determine what type of interaction exists between this system and the universe. First is adiabatic wall. What do you mean by an adiabatic wall? Let us come to this. Adiabatic wall means this wall is completely non-conducting. So, system is insulated from the rest of the universe. System is insulated from the rest of the universe. This implies there is no heat exchange here, no heat exchange. This is called an adiabatic wall. Okay? This is very important. There is no heat exchange. Then how can this system interact with the universe? It can interact with the universe only through mechanical interaction. I can have this wall movable. If I move this wall, then there is some energy supplied to the system. I am doing some work on the system. Okay? That is how it can interact with the rest of the universe. Okay? Then there is a diathermic wall. Diathermic wall is just opposite of what I defined as an adiabatic wall. Diathermic wall on the other hand allows for heat exchange. This is very, very important. one wall is not allowing any heat exchange, system is completely insulated, that is adiabatic wall, system is completely insulated from the rest of the universe. Okay. Diathermic wall on the other hand, it allows for heat exchange. Okay. So, there is mechanical interaction in the case of adiabatic wall which is possible, and then in the diathermic wall there is a thermal interaction possible, that means there is heat exchange, also mechanical interaction is not stopped. So, we can in general have a wall in which you will have both thermal interaction and mechanical interaction, but these are two idealized situations. In one there is no heat exchange possible, in the other heat exchange is possible. Also it is not part of our syllabus, we will not go into that. There could be porous walls which allow for particle exchange. Okay? You can allow particle exchange and then reach some situation when chemical potential of the system and the universe become equal, and then there is an equilibrium reached. Okay? But I will not discuss anything about this chemical interaction, we will restrict ourselves to adiabatic walls and diathermic walls, okay, and talk about thermal interaction means heat exchange and mechanical interaction, that is I am moving this wall of the container. Okay. So, let us proceed. What is equilibrium? Okay. I have told you that there are walls and walls give my interaction. Now, question is what is equilibrium? Equilibrium I defined in the beginning of the kinetic theory lecture also, that nothing depends on time. I measure pressure at time t is equal to T0 if it is P, and then I measure at t is equal to 2 T0, even then pressure will be P, it does not depend on time. Okay. Equilibrium is an idealized concept, but we will always assume that system is in equilibrium and nothing depends on time. So, I define equilibrium constant value of thermodynamic variables, constant in time, they do not change with time. I told you thermal interaction, then that gives me notion of one equilibrium, that is called thermal equilibrium. What is thermal equilibrium? We already know that there is a quantity called temperature. So, I have a system and the rest of the universe, they can exchange heat if it is a diathermic wall, okay? And when they reach the equilibrium, we know basic notion of temperature tells us in equilibrium this temperature of the system should be equal to the temperature of the rest of the universe. So, Ts is equal to Tu. Okay? There is no heat exchange, there is no energy exchange, equilibrium has reached, and since reservoir is very big, I can say I give the term reservoir for you. It is a very big thing, rest of the universe, okay? And I can say it has infinite heat capacity. It is also an idealized concept, but very useful. Infinite heat capacity. If it has infinite heat capacity, its temperature does not change. So, there is exchange of heat between the universe and the system. When equilibrium is reached, temperature of the system will be equal to the temperature of the reservoir, that is the temperature at equilibrium. So, that is thermal equilibrium. So, thermal equilibrium means that temperature is equal between the system and the reservoir. There is no further heat exchange. What is then, let us say, mechanical or adiabatic situation if you like. So, in the mechanical equilibrium what will happen? I will show in more details later that pressure, okay, pressure, I can move this wall of the container there is a pressure of the system, there is a pressure of the universe, I can move this container in such a way, okay, that in equilibrium Ps is equal to P of the universe. So, pressure should be equal. Remember, I am always equating some intensive variables. In one case thermal interaction, it was the temperature, other case mechanical interaction, it is the pressure which becomes equal, and I say there is a mechanical equilibrium, if you like, achieved. Okay? But most of the cases I will be talking about both mechanical and thermal. That means, I will be allowing heat exchange as well as mechanical interactions, okay, and then system reaches an equilibrium and I will do the thermodynamics of that system which is now in equilibrium. So, let me summarize what I said. There are walls, walls are separating the system from the universe. The walls can be diathermic or adiabatic. In the adiabatic situation, there is no heat exchange, diathermic situation there is heat exchange. Walls determined also what type of equilibrium I will have. For example, if I allow heat exchange, then equilibrium will reach when the temperature of the universe will be equal to the temperature of the system. That is equilibrium situation, no further heat exchange, and I can work on with the system which has reached the equilibrium. Similarly, one can talk about a mechanical equilibrium in which the wall of the container is movable. I move it in such a way that pressure is balanced, pressure is same between the system and the universe, that is the mechanical equilibrium. Okay? And I will be talking about situation which has reached mechanical thermal equilibrium, nothing depends on time, and then I will do the thermodynamics of that particular system. Okay? Now, having said all this, walls, mechanical interaction, heat exchange, I will establish for you, rather I will propose the first law of thermodynamics, and as I said, first law of thermodynamics is nothing but the conservation of energy. If you remember, these I mentioned maybe in my second lecture. So, first let me consider a container. Inside that you can assume these gas molecules I have been talking about in kinetic theory, they are moving around, but in thermodynamics I do not want to know their velocity distribution. Okay? Now, let us say I supply an amount of heat delta Q, or let me use this notation delta Q. Okay? An amount of heat delta Q I supply to this system. What would happen to this system? Its energy goes up, but if I do not allow any mechanical interaction, okay, I do not allow any change in volume, what will happen to this energy supplied to the gas system? Something should increase. That is why conservation of energy tells me energy cannot be dissipated. Okay? So, you have to keep in mind something additional is there other than mechanical energy and thermal energy I have been talking about. So, first I can change energy by supplying heat, then forget about heat, which I already explained. You move this wall, with some velocity u. So, what will happen? This is moved, okay. You can roughly think that molecules coming with some velocity here hitting the wall, but unlike kinetic theory where I was assuming this wall is a static object, these molecules will not go back with the same velocity or same speed, because there is now a relative velocity, wall is also moving. Okay? So, since wall is also moving, the molecule which hit this wall will go back with a different speed. So, its kinetic energy changes. Okay? This is a very heuristic, very phenomenological idea, but all I wanted to say, by doing this mechanical work, by moving the wall of the container, I am changing the energy of the system. So, energy of the system can be changed in two ways. One, by supplying or extracting heat. I can take heat away from the system, or I can supply some heat to the system, energy increases. And then this mechanical part of the energy, which tells me if I move the wall, okay, if I move the wall, what will happen? That energy will change, that I very roughly, very approximately said that if molecules coming with average speed v, they will not go back after hitting the wall with the same average speed. There will be a change, because this fellow, the wall itself is moving with a velocity u. So, there is a change in energy. So, change in energy can be achieved also due to mechanical work. This is what I learnt in mechanics. Okay? I do some work, okay? So, I get some change in energy. Now, question is, I am changing. How? What is the process? Am I changing the wall of container very fast, very rapidly? Okay, that is not true. I am not really doing that. All the processes I have talked about heat exchange, I have talked about mechanical interaction in which I change the wall of the container, move the wall of the container, but I am not doing it very, very rapidly. This brings in the concept of quasi-static process. Okay? What is a quasi-static process? Quasi-static process means it is a very, very slow process. How slow is slow, you can ask me? It is very slow in the sense you draw a PV diagram, right? You have a PV diagram. Okay? Given a P, you always give me a value of V. I choose a value of P, I immediately get a value of volume V. Okay? And I expect them to satisfy the equation for an ideal gas PV is equal to RT. And I said this equation is valid only in the equilibrium. So, quasi-static process is a process, you should understand it is quasi-static, that means almost static. I am changing the parameters, be it movement of wall or supply of heat, very, very slowly. There is an infinitesimal change, slower than any other characteristics time scales of the problem. Okay? Any other characteristic time scale of the problem, which is very slow. More importantly, I am making a change, but every instant I can assume that system is in equilibrium. So, this is a quasi-static process. A quasi-static process means it is a very slow process, and every instant of time I can assume system is in equilibrium. For an ideal gas, I can write PV is equal to RT. Okay? This is very important notion which will keep coming back to. Okay? So, whatever changes I mentioned here are all quasi-static changes. Whatever I am saying will completely break down if I do very rapid process. Okay? What happens if I do a rapid process? Okay? There will be final state reached, I have to wait for the system to equilibrate. When system equilibrates, once again all thermodynamic variables reach a time independent value, I can do thermodynamics. But in between what happened? I do not know. But what is the difference in the PV diagram? At every instant of time, I am assuming that system is in equilibrium and I can write PV is equal to RT. So, this is a very important notion. Walls, equilibrium, and to be always in equilibrium, I need quasi-static processes. Whatever process, mechanical, thermal, I am talking about are all quasi-static processes. Okay. Now, I have said that there are two types of energy which I will talk about. One is thermal exchange, exchange of heat. I wrote it as delta Q. Let me say the mechanical work, this is delta W. Okay. Now, should I then say delta Q is equal to delta W and that is my energy conservation? No, I will be in trouble, because here I am just allowing exchange of heat. There is no work done on this system. So, heat must go to some other form of energy. Okay? This point should be clear. Here I am not talking about any work, no work. If no work, there is no mechanical energy. So, there must exist some other form of energy in which the heat is getting converted to. Similarly, here if I do not allow any heat exchange, what would happen? There must be some other form of energy to which this mechanical energy is going. Okay? Remember, here if no work is done in this process, I am supplying heat, some energy of the gas must go up and that energy is called the internal energy. Okay? This is a very important concept, that if you do not do any work here, system is not allowed to do any work. So, where does the heat energy go? Heat energy goes in increasing the so called internal energy of the system. Similarly, here if you do not allow any heat exchange, the mechanical work that you do on the system goes on to increasing the internal energy of the system. So, this is first fundamental notation or fundamental concept which I brought in, which is called the concept of internal energy. So, when you talk about conservation of energy, when you talk about this conservation of energy, please remember the conservation of energy includes heat energy, thermal energy, here mechanical energy, here or the work done, and the change in internal energy. With all this preamble, system, reservoir, walls, interactions, okay, notion of internal energy, quasi-static processes, I now put before you what is the first law of thermodynamics. This is the first law of thermodynamics which is written out on this slide. You can see delta Q, heat supplied to the system. I am supplying an amount of heat which is delta Q, and then delta W is the work done by the system. See, previous example I took two extreme cases. Here I said heat supplied, no work. Here I said I am doing some mechanical work on the system, not allowing any heat exchange. Here I am doing both. That is why in one of the previous slides I said that I will be talking about both mechanical and thermal interactions, and then system reaches the equilibrium. I will deal with that particular system and do heat exchange or mechanical interaction in a very quasi-static way, so that I can always assume that system is in equilibrium. So, delta Q is the heat supplied to the system, delta W work done by the system, and then first law of thermodynamics said delta Q is equal to delta W plus this new quantity which is called delta U, that I will be calling the internal energy. Okay? So, you see, if delta W is 0, first example of the previous slide, delta Q is delta U. So, whatever heat I supplied went into increasing this internal energy. Okay? And then if I do some work, but do not allow, okay, do not allow any heat exchange, so that delta Q is 0. So, you see delta U is equal to minus delta W, okay, minus delta W, and this is where I need to fix a convention. Okay. I will fix a convention in the following way: delta Q positive when heat is supplied to the system, internal energy increases, delta W is positive, work done by the system. Okay. In the previous example, if I was doing some work, okay, on the system, then it would be negative and internal energy goes up. So, I repeat the first law of thermodynamics: delta Q heat supplied to the system, delta W work done by the system, okay, and then again I write it in the form which is written here, that is delta Q is equal to delta U plus delta W. Okay. Convention is delta Q is positive, heat supplied to the system. Heat is extracted from the system, delta Q will be negative. Okay. If you set delta W is equal to 0, delta Q is equal to delta U. So, whatever heat you supply to the system, it goes into increasing the internal energy of the system. If you extract heat from the system, then delta Q is negative, internal energy goes down. Okay. And now, other way around, if we talk about this one, you can see from this expression, in one case internal energy will increase when I work on the system. Okay. Then this delta W itself will be negative. From the equation for the first law of thermodynamics, I get this one. If delta W is negative, means I am working on the system, internal energy increases. If delta W is positive, that means system is working at the cost of its internal energy. So, you see, for energy conservation, internal energy must be there. We should understand what is this internal energy. Okay. Before I proceed to that, let me write it in the following form. The first law of thermodynamics, what I have written here, which is actually conservation of three quantities: thermal energy, work done or mechanical energy, and the internal energy, can be written in a differential form. Okay. It says delta Q, delta W and du. This is where one has to be careful. Why these two are delta and this one is d? These I will explain briefly today and elaborately in the next lecture. But let me proceed a little bit. What is the internal energy? I said if supply heat to the system and do not let it work, its internal energy goes up. What is this internal energy? Okay. You know, if you supply heat, kinetic theory has already told me that average kinetic energy increases, which implies that temperature increases. Okay. Without further proof at the moment, I will just say, let us say ideal gas molecules, let us say monoatomic. If it is monoatomic, okay, I know the translational kinetic energy. If I take, let us say, 1 mole of monoatomic ideal gas, 3 by 2 n kBt, here it is the Avogadro number which we kept referring to. So, this translational kinetic energy is actually the internal energy. How do you know this analogy clearly? You know this analogy clearly because you know when you supply heat, temperature increases. Kinetic theory teaches us that average kinetic energy increases, translational kinetic energy, ideal gas, monoatomic, only translational. So, for monoatomic ideal gas, it is the translational kinetic energy, that is the internal energy. So, you increase the temperature, what goes up is the translational kinetic energy of the monoatomic gas molecules. Okay. So, what is internal energy? Internal energy is equal to this form, which I will not prove probably, but I will expect because of this analogy, it is CVT plus constant for ideal gas. And you know CV has the information whether ideal gas is monoatomic, diatomic or polyatomic. I count the degrees of freedom taking either translational or translational plus rotational or translational plus rotational plus vibrational. All those informations go into this CV. So, it is the kinetic energy if you talk about ideal gas molecules. Okay. This is a good point, I think, where we should stop, but I have to tell you this is a very important thing, this delta Q, delta W and dU. Actually delta Q and delta W, they depend on the thermodynamic processes. I have already shown you 2 examples in which I have, in one I have delta Q is equal to 0, only delta W was there. In the other there was a delta Q but no delta W. So, this delta Q and delta W, if I go from a initial state to final state, okay, let us say this is Pi, this is Pf, I go from an initial to final state, let me Pi to Pf, okay, or Vi to Vf. This delta Q and delta W depend on how I have reached from the initial to the final state, but dU does not depend on how I went from the initial to the final state. Rather, it depends upon only the initial state and the final state. Okay? That is a very important concept which I will explain from the point of view of mechanics, where you already know there is a concept of potential for a conservative force field. That I will generalize here to explain to you what is this internal energy and what do I mean by the terminology that it is a state function. So, I end this by saying that this quantity actually is a state function. This quantity U is actually a state function, depends on initial and final state. That means, initial and final values of the thermodynamic variables. If it is ideal gas, I already have tried to explain to you that it is CVT. So, it will actually be given by the difference in temperature of these 2 states. Okay? Thank you for today.